All right, so next topic is message authentication codes. Since we have seen block ciphers and hash functions, actually it is a good time to talk about message authentication codes. But know that this is not an encryption, okay? This is authentication. So idea is as follows. Communicating parties share a secret key K and they can compute an authentication tag T using K, okay? Sender computes T and sends it with the message. So here the message is not secret. You simply send the message, but concatenate a tag to it, saying that this is the authentication code for it. The receiver can verify the message, whether the message has been altered or not, by computing the tag T prime from the message they received and check if T equals to T prime. And that's it. This way you provide authentication. And see, you only shared the secret key with the person or people you want to communicate. You know that the data origin is authenticated this way, okay? Because nobody else can provide such a tag without the secret key. This is what you offer a message authentication code. So in this scenario, you can perform two different kinds of attacks. Since this message authentication codes use a secret key, of course, the main way of attacking is to recover the secret key, right? So in this scenario, you have n many message tag pairs. Like for instance, M1 has the tag T1, M1 has the tag TN. So you listen to communication, capture all of these tags and messages since they are not secret. But it should be infeasible for an attacker to recover K with secret key K that was used to create these tags, okay? So this is the idea. The key recovery is to capture the secret key from these messages and tag pairs. But there's another way of attacking it without capturing the secret key, which we call MAC forgery. So MAC is here for message authentication code. So in cryptography, when we say MAC, this is what we understand. But in networks, when we say MAC, this is media access control and that kind of stuff. So don't confuse them. But here the forgery works like this. Assume that you obtain many message tag pairs and many. Then it should be infeasible for an attacker to generate any valid message pair M prime T prime, where M prime is not one of these MIs. So you shouldn't be able to produce a tag for a message that wasn't sent before. Okay, and sometimes it is possible. I mean, without recovering the secret key, sometimes you can do it if the algorithm is not secure enough. So a key recovery attack should require 2 to the K operations. Key recovery attacks lead to MAC forgery, but for a weak scheme, it may be possible to forge a tag without recovering the key. If the message authentication tag T is of T bits, a successful MAC forgery should require 2 to the T operations. Okay. Again, this is for the upper bound security like brute force attacks. So let me show you how you can obtain some kind of message authentication code from block ciphers, okay? So assume that you have an encryption algorithm here. We can think AES for simplicity. So it uses a secret key. So this is the message you want to authenticate, right? So you send this message, but you also divide it into blocks and perform these encryption operations, okay? Then at the final encryption, you do some finalization process and obtain T, the tag. So motivation is as follows. Last ciphertext block is dependent on the previous plaintext blocks in CBC mode, right? So this is what we call CBC MAC. So I'm not producing any ciphertext, but I'm using the block cipher in CBC mode to produce message authentication code. So CBC MAC appears in FIPS with DES being the underlying block cipher. So it is a very old standard, but of course you can update it with AES. But note that the block size actually determines the tag size. So if you're using AES here, the tag will be of 128 bits. Again, the final process is necessary to avoid forgery attacks. There are other variants like CMAC or OMAC, which is called one key MAC, and the picture is like this. You do the similar stuff, but you also use the key to derive some tweak values and obtain XOR them here and so on. So this is your tag. So these are used in some protocols. I'm not going into detail, but the idea is similar, okay? But there's something more popular called HMAC. So until now, I showed you 2 examples where we use block ciphers. Now I'm going to use a hash function. So H here can be SHA-1, SHA-2, whatever you prefer. So idea is as follows. This is the message you want to authenticate. You have a secret key. You perform an XOR operation with an iPad, which actually fixed value. You just XORing it. You can even look at it in Wikipedia. So you XOR your secret key with iPad and concatenate the whole message to it, then calculate the hash of it. Then you don't stop here. You do the similar operation with this time with a different padding, then calculate the hash again. So in HMAC, you calculate the hash twice, but the second hash operation is negligible compared to this. For instance, assume that your message is 1 gigabytes, okay? So since you are going to divide it into blocks when you are using SHA-256 or anything, it takes a lot of time to calculate this hash. But once you calculate this hash, the output is short, like 256. So calculating this final hash most of the time is negligible compared to this. And of course, if the message size is small, then these take the same amount of time, but most of the time, this is negligible, okay? So actually here, I said that SHA-1 is not secure since we can provide collision attacks, but if you use SHA-1 with HMAC, then the collision attacks wouldn't bother you here, right? So you can use SHA-1 HMAC. So there are also lightweight message authentication codes, which are ISO standards. There are 3 of them. These are standards from 2019, but these standards were reviewed, I think, in 2022, so they're still valid. None of them are removed or changed. So these are LightMAC, SUDIX, Keymode, and Chasqui TWAF. So if you're interested for lightweight message authentication codes, you can check them.